Hello. Now we'll start with exploring relational data in Azure. Let's start with the introduction. In the early years of computing systems, every application stored data in its own unique structure. When developers wanted to build applications to use that data, they had to know a lot about the particular data structure to find the data they needed. These structures were inefficient, hard to maintain, and hard to optimize for good application performance. The relational database model was designed to solve the problem of multiple arbitrary data structures. The relational model that provides a standard way of representing and querying data that can be used by any application. One of the key advantages of the relational database model is its use of tables, which are intuitive, efficient, flexible way to store and access structured information. The simple yet powerful relational model is used by organizations of all types and sizes for a broad variety of information management needs. Relational databases are used to track inventories, process e-commerce transactions, manage amounts of mission-critical customer information, and much more. A relational database is useful for storing any information containing related data elements that must be organized in a rules-based consistent structure. In this module, you'll learn about the key characteristics of relational databases and explore a relational data structures. Okay, now let's start with understanding relational data. In a relational database, you model collections of entities from the real world as tables. An entity can be anything for which you want to record information, typically of important objects and events. For example, in a retail system example, here, you may create tables for customers, products, orders, and line items. Within an order. A table contains rows, 1, 2, and each row represents a single instance of an entity. This Joe is a single instance of the customer. In the retail scenario, each row in the customer table contains the data for a single customer. This is the data for a single customer. Each row in the product table defines a single product. Each row defines a single product. Each row in the order table represents an order made by a customer. Order number, this is the order, and each row in the line item table represents a product that was included in an order. For example, here in order number, we have the same order. Okay, order number 1000. What does order 1000 have? Item number 1 and 2, product 123, 201, and quantity. As we can see here, this is a little bit special, but I'm not going to mention it. Each row in the order table represents an order made, and each row in the line table represents a product that was included in an order. We all will know one thing in line item, no two rows are similar. No two rows are similar, 100% similar. No two rows are 100% similar. It might be similar to a certain degree, but no, not every single not no two rows are same. Relational tables are a format for structured data, and each row in a table has the same columns. So in some cases, not all columns need to have a value. For example, a customer table might include a middle name column which can be empty or null for rows that represent customer with no middle name or whose middle name is unknown. For example, here middle name, as we see Samer Nadoy, he doesn't have his middle name isn't present. It might be null or it's null now because we don't know it or he doesn't have one. Each column stores data of a specific data type. For example, an email column in a customer table would likely be defined to store character-based text data, which might be fixed or variable in length. Here, we'll have this is the data type that stores length emails. A price column in a product table might be defined to store decimal numerical data, as we see here. While a quantity column in an order table might be considered to integer numeric values, for example here, quantity here. And an order date column in the same order table would be defined to store date time values. The available data types, as we can see here, the available data types that you can use when defining a date table depend on the database system you are using. Though there are standard data types defined by the American National Standards and Institute that are supported by most database systems. So basically, there are the data types differ between each system, but there are standard data types, which is defined by the ANSI Institute, American National Standards Institute. Now, let's read more about normalization. What is normalization? Normalization is a term used by database professionals for a schema design process that minimizes data duplication and enforces data integrity. While there are many complex rules that define the process of refactoring data into various levels or forms of normalization, a simple definition for practical purposes is: separate each entity into its own table, separate each discrete attribute into its own column, uniquely identify each entity instance row using a primary key, use foreign keys to link related items. Separate each entity. We have this entity, sales data, it has its own table. Each discrete attribute, order number is an attribute, order date is an attribute, it's all separated into its own column. Uniquely identify each entity instance. Each row using a primary key. We'll have a primary key. I'm not sure if sales data order number is the no, it's not the primary key here. Use foreign key columns to link related entities. For example, the entity here, foreign key order number, we got it from a previous table. We'll read more about it here. One second. To understand the key principles of normalization, suppose the following table represents a spreadsheet that the company uses to track its sales. Notice that the customer and product details are duplicated for each individual item sold, and the customer name and postal address and the product name and prices are combined in the same spreadsheet cells. For example, the product, it's combined here. The customer, it has data combined here. Now let's look at how normalization changes the way the data is stored. For example here, the customer, Joe Jones, it's all connected to each other, but it's all individually how this is how it's all individually stored. Now, each entity that is represented in the data customer, product, sales, order, and item is stored in its own table, and each discrete attribute of these entities is in its own column. Okay? Attributes are in its own columns. Each entity has its own table. Recording each instance of an entity as a row in an entity-specific table removes duplication of data. For example, to change a customer's address, you need only modify the value in a single row. For example, here the address, I need to change it. I don't need to change everything. I only need to change that specific address. The decomposition of attributes into individual columns ensure that each value is constrained to an appropriate data type. For example, here, the data attribute, here, the data type is integer, 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 integer. Here it's date. Each column has its own data type, and here it's date, integer, integer, text, integer, decimals, and so on. For example, product prices must be decimal values, while line item quantities must be integer numbers. Additionally, the creation of individual columns provides a useful level of granularity on the data for querying. For example, you can easily filter customers to those who live in a specific city. Here we see additionally the creation of individual columns provides a useful level of granularity in the data for querying. Now each column has its own, it makes querying easier and better. For example, you can easily filter customers to those who live in a specific city. For example, I have a million customers and I need to point people who live in a certain city. I can just make when I select when I query, I'll just make the address to a specific city and it would show me all the customers in that specific city. Instances of each entity are uniquely identified by an ID or other key value known as a primary key. And when one entity references another, for example, an order has an associated customer, here we'll see order, order number, this is a primary key, but this customer, it's referring to Joe Jones. So this is referring, this is called the foreign key, while this is called the primary key. A primary key is not present twice in a single column. The primary key of the related entity is stored as a foreign key. Here, this is the primary key of the customer. It's stored as a foreign key in the order. You can look up the address of the customer, which is stored only once for each record in the order table by referencing the corresponding record in the customer table. For example, I can look up the address of the customer when I take this customer ID. It's referencing Joe Jones, and I'll figure out his address. Typically, a relational database management system (RDBMS) can enforce referential integrity to ensure that a value entered into a foreign key field has an existing corresponding primary key in the related table. For example, preventing orders for non-existent customers. Instances of each entity are uniquely identified by an ID or another value. I mentioned it could be an ID or anything else. When one entity references another, for example, an order is stored as a foreign key, you can look up the address of the customer, which is stored only once for each record mentioned. Can enforce referential integrity to ensure that a value entered into a foreign key field has an existing corresponding primary key in the related table. So this is constraints. Basically, it's mentioning constraints that quantity. For example, here the product ID, you don't mention 123 unless it exists here. So if 123 doesn't exist in product, we don't place it here. We don't use it here. It's for example, preventing orders for non-existing customers. In some cases, a key, primary or foreign, can be defined as a composite key based on a unique combination of multiple columns. For example, the line item table in the example above uses a unique combination of order number and item number to identify a line item for from an individual order. Here, line item in the table in the example of uses a unique combination of order number and item number. We'll see here order number and item number. Here it's used to make it its composite primary key. We use it to make sure that no two columns are the same. Wait a second. Order number and item number. I'm sorry. Order number and item number. Here in line item order, this is the one. Order number and item number, we use it as a composite primary key so to make sure that no two rows are the same thing. Thanks for watching, and we'll start with the exploring SQL in the next one, in the next video.